Okay, this is lecture 11, part 1 of, I don't know how many parts there will be, I think 3, reaction stoichiometry. We are going to be using our balanced equations and the mole-to-mole ratios to answer all kinds of questions about how much something we make, how much of something we need, etc. So mostly working problems. So we'll start with the slides. All right, so our balanced equation, let's see if I can go back and find one. So I think it's this one down here is balanced. So that when it's properly balanced, you see the number of moles of each molecule or compound in your reaction. And you can use those molar ratios. 2 moles of potassium chlorate generates 2 moles of potassium chloride and 3 moles of oxygen gas. You can use these numbers mathematically and this molar relationship to come up with all kinds of calculations and answers of how much of something is produced and how much of something is used up. And you can also do ratios within. I could get a relationship using just the chlorine atoms. You can ask any question you want as long as it's within a balanced chemical reaction equation. So we're going to do that. So mole-to-mole ratios, the stoichiometry tells the ratio of one compound to another in a reaction equation, a balanced one. And we use them as conversion factors. In the past, you've used conversion factors that are identified grams per mole, Avogadro's number. We've given you unit conversions of standard to metric. Okay, this time you're going to be using conversion factors from the relationship in a balanced chemical equation. So if we look at a balanced chemical equation, you can talk about atoms and molecules. These would all be molecules, individuals, but we don't work with individual molecules. We don't weigh individual molecules in the lab. We weigh moles. So therefore, you would look at this as a molar ratio because that's what we actually can use in the lab. But following one of Dalton's postulates, the matter is neither made or destroyed. In other words, the number of atoms on the left side has got to equal the number of atoms on the right. Remember, this is the reactants, the left side. The right side is the products. So your mass of the left and right have to be the same because the number of atoms on the left have to be the same as the ones on the right. So they'll have the same mass, left and right. But we're going to use the molar ratios. So mostly I'm going to be working through a number of calculations, equations, questions. You're going to start getting these more in-depth questions. Mind you. All right, so this is the first one. We have this balanced reaction. And then we have some questions to ask. You will be given a certain amount of at least one of your, well, in this case, it's a reactant. You can be given a product amount and have to work backwards. Notice that this reaction has energy in it. As I said, sometimes if energy is, this is an exothermic reaction. So sometimes we put the energy in the reaction. It's exothermic, it's releasing heat. And so there's the energy that it's releasing. The amount that it's releasing is actually a specific amount. It has to do with the bond energy. If it were endothermic, you would put the energy over here as a reactant. And it's just as much a part of the reactant as this molecule and this molecule. This is just as much a product as this and this. We just don't call this moles. This is kilojoules. A joule is an energy unit. Kilo is 1,000. So this is 200,000 joules or 200 kilojoules. So I'll show you how you use that. You really just pick it up and put it in with your conversion. So we're going to ask if you have a certain amount of propane, which is here, how many moles of oxygen do you need to use up all that propane? And then we're going to find out how much product do you produce, and then how much energy, which is a product, is released. So how much energy do you make? So let's go to the whiteboard. All right, so now I'm not going to include the phases. Normally we do, just because I have very little space. That's not very dark. I already need new pens. So this is propane. So 1 propane, we don't put the 1 in front. I know that the one slide shows you, the slide I was just looking at has a 1, but that's just to, as an example, to point out to you how we're using these. We really don't put a 1 as a coefficient. Okay, I'm gonna have to move things around. I always run out of room. Put me down here. Okay, propane, 1 mole propane, 5 moles of oxygen gas produce, it's a combustion reaction, 3 moles of carbon dioxide and 4 moles of water vapor, and releases 200 kilojoules of energy. For this specific ratio, you get that much energy. So what's the question? The question says I have 6.38 moles of propane, and it says how many moles of oxygen do I need to completely consume this? Okay, so the first thing you do is you start with what you have. They gave us this. Now notice this is 3 sig figs. That is probably going to determine your answer, sig figs. It's probably going to have to be 3. Because these numbers, when we use them in conversions, are exact numbers. They are not used for sig figs. These are called exact numbers, these coefficients. So 6.38 moles. Make sure you put the identity, whoops, and the units. Okay, we're going to go from moles of propane to moles of oxygen. All right, that will cross out our propane. That will give us what it's asking for. And now we just put numbers in. Where do we get these numbers? We get them from this reaction. All these new conversions you're going to be able to do come from this reaction relationship. So for every 1 mole of propane in my reaction, I have to use 5 moles of oxygen. All right, that's where these come from. Let me find my slide. Whoops. So I multiply 6.38 times 5, and the answer is 31.9 moles of oxygen. Notice that's in 3 sig figs, because that's in 3 sig figs. You have 3 here. This does not count towards sig figs. It's exact numbers. So that's a simple question. I have moles. It's asking for moles. You simply look at the reaction equation. Okay. The next question is, I have this same 6.38 moles of propane, but it wants to know how much carbon dioxide is increased. Now it just says how much, but I'm going to assume that the slide means moles, because right now we're keeping it simple. So again, start with what you have. Right, this is what the problem gave us. It's the same number of moles. This time, when I get rid of my moles of propane, it's asking me for moles of carbon dioxide, so that goes on top. Okay, yes, this will cancel out. It will give me what I'm looking for, so now we put numbers in. Again, I have 1 mole of propane for every 3 moles of carbon dioxide, or you can say 3 moles of carbon dioxide are produced for every 1 mole propane consumed, however you want to phrase it. So you multiply 6.38 times 3, and I don't think I have that handy. All right, let me get my handy little calculator. So 6.38 times 3 is 19.14 moles of CO2. I have 3 sig figs. This does not count. So my answer will be in 3 sig figs. So it'll be 19.1 moles of carbon dioxide are produced. Okay, that's pretty easy. Now it's asking how much energy is produced. It's just as easy. It is literally just as easy as these others. We're sticking with the same amount that we started with, so the 6.38 moles of propane. You still put the moles of propane. This is the relationship. We're using this reaction equation, so it's the molar relationship in here. It's just that for energy, we put kilojoules because that's our energy unit. Go back in here. What are my numbers? 1 mole of propane and 200 kilojoules. In other words, in this reaction, that's the number for the energy. Pull it out. Cancel that out, and I get these, and you multiply those two numbers, and it's 200 times 6.38 equals 1276 kilojoules. I do not know if this is 3 figs, sig figs, or 1. If I ever give this to you on a test, I will make it obvious how many sig figs is, because this is a number that would be variable. This is not an exact number, so I'm gonna call it 3. I'll make a executive decision here, which means, and that's 3, so it will be 1280 kilojoules. If I had said it was 1 sig fig, then my answer would have to be 1 sig fig, and it would have to be 1,000. But that's how you use, the more important part of the question is, how do you use the energy? You just pop that in, just like you pop any of these other relationships in. So to go back to show you the slide, to show you what I was working with, when you go back and look at this, you'll know what to follow along with. So it's this slide that I just worked through. And then if you go down a couple, because it's a little bit out of order here, here's the answer to one of the questions. And that's a different one. Okay, never mind. So anyways, this is the slide that I was just working through. All right, let's look at this down here at the bottom. Like I said, there are lots of problems you can work through, and I highly recommend it, because the more you work these problems, the more comfortable you will get with it. So this is using the same equation, so that's handy. Okay. So let's go back to the whiteboard. And I'll pull this up on my other computer. Okay, so we're still using this equation, little dots. But this time the question is, how many grams of oxygen, so the question is grams of oxygen, are needed to react with 63.8 grams of propane. Okay, this time you are not in moles, you are given grams. Anytime you are given grams in stoichiometry problems, the very first thing you should think of is, I have to convert something to moles. That should be the very first thing. Even if you don't know what yet you're going to convert, the very first thing you should think is, I have to convert something to moles, because you cannot do ratios with grams. You just can't. This is molar. That's why the mole is so important. So the very first thing we're going to do is convert something to grams. Well, what do I have with grams? I have propane. So when in doubt, convert to grams. You're probably on the right path. And using the slide that I'm looking at, so I don't have to go add everything up, make sure my grams cancel out. I have a really bad habit of putting this upside down or putting the number at the top. That's why I always put the 1 as an anchor. So that's one of my things to check. So then we have 63.8 divided by 44.09. But I'm not done because I haven't answered my question. All I've done is change to moles. But now that I'm in moles, I can start converting anything in this reaction equation. The question is about oxygen. So let's go from propane to oxygen. That's the next step. Now we're going to change identities. And the video camera is in the way again. And we want oxygen. So we're replacing propane with oxygen with the relationship described in this equation. What are our numbers this time? And I know I said normally I don't put numbers in until I get my units correct. I just know where this is going. So in this reaction, I have 1 mole of propane for every 5 moles of oxygen. Okay, now we're in oxygen. Okay, but the question did not ask for moles, it asked for grams. Very important to go back and look at what the question is asking, or you will get it wrong, especially if it's multiple choice. There is no partial credit on the final. So I have moles of oxygen. I now need grams of oxygen. So of course, we're going to put our moles down here and our grams, that's the molar mass. So it's 1 and 32. I have 3 sig figs here. I have 4. This does not count. I have 4. So my final answer will be in 3 sig figs. And I do the math, and it's 231 grams of oxygen. So we have our answer is 231. Okay, you can also ask the question of how many grams of carbon dioxide are produced. Well, I'm going to keep my first step because I have to go to moles. And because I'm still using the same amount of propane we were given, it's the same problem, I'm keeping the first part. So I have moles of propane, but now the question is carbon dioxide. Well, first you have to get to the identity. And so you're going to go from moles of propane to moles of carbon dioxide. Because again, if you are in moles, you can do this. Mole to mole, no problem. You cannot do it with anything else. In this reaction equation, I have 1 mole of propane. How many moles of carbon dioxide? I have 3. Okay, I am now in carbon dioxide, awesome. But the question did not ask for moles, it asked for grams. So we use the molar mass conversion to go from moles of carbon dioxide to grams of carbon dioxide. And for every 1 mole, it's 44.01 grams. Great. Now I've got what the question asked for. 3 sig figs, 4 sig figs, that doesn't count. It's exact numbers, 4 sig figs. My answer will be in 3 sig figs. And when I do the math, it's 191 grams of carbon dioxide. So that's the answer to my question. I'm going to go back to the slide and show you where that was. So as you go back and work through these, you know where I'm finding them. It's this slide. So we did this one, and this is the next slide, and it's this box down here that I just worked through. So this slide is just talking about, it doesn't matter, anything can be written in a relationship, and it doesn't matter what's on top and what's on bottom. As long as your relationship is true, your numbers are correct, you can relate anything in here. Like I said, you can even do the atoms. You can pull the oxygen atoms out and ask a question about that. As long as it's, you know, is coming from this relationship and your numbers are correct that you use, you can ask anything. With moles, you have to be comparing moles and moles. So this was one that we already worked out. Okay, so here's another one coming at it. We've been doing propane. Well, now we're given the amount of oxygen, right? It's already in moles, so that's really good. All we have to do is change identity. So I will work it out, but you should pause right now and you should work this out and then come back on. Okay, so back to the whiteboard. We're with the same reaction, so that makes it convenient. Yep, I just erased part of my reaction equation. Okay. So this time it says, what are we given? And write down what you're given and write down what you're looking for. They're very important focal points, especially as we get more and more detailed. So it says we have 8.42 moles of oxygen. And the question is moles of propane. All right. Well, start with what you got. Moles of oxygen. I do not need to convert to moles. They already did it. That's very handy. But I need to change identity. So moles of oxygen goes on the bottom. Moles of propane goes on top. All right, that will cancel out my units. And so that's what I'm looking for. What are my numbers? You go to your reaction equation. How many moles of oxygen am I going to put here? You're going to put 5. Because that's the relationship. How many moles of propane? 1, our invisible 1 there. That's all you do. Now you just divide 8.42 by 5 because it's 8, 8 times 1 divided by 5. And the answer is less. Okay. So go ahead and work it. 8 point, whoops, that's not it. 8.42 divided by 5. Now we have 3 sig figs here. These do not count for sig figs. Get 1.684 moles, but we have 3 sig figs. So my answer is 1.68 moles of propane. And if we go back to that slide, because the following slide has oh no, that slide has the multiple choice. And it's right here, D. So the answer is D, if you work this out, which you should. Okay, so I worked this problem out, I think. So we'll do this one. This is asking how many moles of water will be produced. That's a product. And we are still with the same 8.42 moles of oxygen. So we're still, this is an extension of the first question. And often this is what you get. You get a series of questions. So I'm still going to use, it's still the 8.42 moles of oxygen. But this time the question is, how many moles of water? Well, water is a product. So I'm going to stay with what I have, my 8.42, but my relationship this time is with the water, 5 oxygen, of course, and I'm going to put 4 moles of water. And that's all you have to do. So it's 8.42 times 4 divided by 5. We say 8.42 times 4 equals, divided by 5 equals, and I get 6.736 moles of water. However, I have 3 sig figs. These do not count as sig figs. They are exact numbers. So my answer will be in 3 sig figs. That 6 is going to round up my 3. So my answer is 6.74 moles of water. And if we go back to the slide, because it's a multiple choice slide, I believe. Yes. So it's 6.74. So the answer is E. So this is called, when you are calculating the product. So when you're calculating carbon dioxide or water or energy in this reaction equation, what you're calculating is called the theoretical yield. Yield is what you produce. That's just the word yield means what you make. Okay? It's just the word we use. What's your yield? How much product did you make? Theoretical is because you're calculating this. This is, in a perfect world, this is what you'll get. However, we rarely are in a perfect world. Most of the time you do an experiment, you are not going to produce exactly what you calculated out. Some kind of human error, some kind of real world interference is going to occur. Usually you will have a smaller yield. Sometimes you can have greater because if what you're calculating is by mass, you're weighing it, you might have a contaminant that actually makes it way heavier. What you actually produce in real life is called the actual yield. We're going to use that in a bit. But whenever we calculate the amount of product that should be made with a given amount of reactant, what we calculate is called the theoretical yield. And then we compare what we actually got to that to get a percent. A percent yield. But I'll get to that. I don't remember if I worked this out or not, so if I did, well, I don't think I did. If I did, I'll do it again. So, because I did it earlier in class. This time we're starting with grams and it's asking for grams. All right, so back to the whiteboard. So we are using the same reaction equation, which is convenient. What are we given this time? This time we're given 63.8 grams. Did I work this out? Hang on. Bear with me. Go back and look at my slides a minute. Okay, no, it was a similar one. And if I did, we'll see it again. Okay. So 63.8 grams of propane is how much you're given. And the question is, how many grams of carbon dioxide will you produce? And of course, this will be a theoretical yield. You're calculating it. It's in a perfect world in theory. When you go in the factory and you produce this carbon dioxide, you probably won't get exactly this amount. What do I do first? When you see gram, you should immediately think, I have to convert something to moles. Or when in doubt, convert something to moles. So let's convert something to moles. Because we can't do anything with grams with reaction stoichiometry. So for every 1 mole, it's 44.09 grams. Okay. Now what do I do? I'm in moles. Now that I'm in moles, I can relate this moles of propane with anything in here. It's asking for CO2, so let's convert it to CO2. So you change identity with the molar relationship. I can go from moles of propane to moles of carbon dioxide using this relationship. I have 1 mole of propane. I have 3 moles of carbon dioxide. Okay, now I'm in carbon dioxide. However, the question asks for grams. So you have to come over here and convert back to grams. You have stepping stones. What I'm getting rid of goes on the bottom. What I want goes on the top. Bottom and top because it's opposite what I'm getting rid of. On a few rare occasions, you will be asked to get rid of something that's on the bottom, in which case your crossover has to be on the top of your next relationship. Because we're always going, across. So 3 moles of CO2 is on the top here. My moles of CO2 are on the bottom. Therefore, they cancel out. For every 1 mole, I have 44.01 grams of CO2. Do all my math. I have 3 sig figs here, 4 here, 4 here. I'm multiplying and dividing. So you count 1, 2, 3, and my answer will be in 3 sig figs. So I will make 191 grams of CO2. So that is my theoretical yield. Right there. Okay, this is the same type of question, but this time we're starting with the other reactant, with oxygen. So it doesn't really matter what you start with, and you can work backwards. If you're given an amount of product and asked something about the reactant, you handle it the same way. Make sure you're in moles, and then you just change your unit or your identity. First, you change your identity using the relationship, the molar relationship in the chemical equation, in this chemical equation here. So back to the whiteboard. So this time the question is on the next slide. It says we have 7.95 grams of oxygen, and it says how many grams of water will be produced. So this will give us a theoretical yield of water. What's the first thing you do? What have you got? You have grams. The very first thing you should think of is convert something to moles. So let's convert something to moles. That's the only thing we're given. So let's do that. grams to moles of oxygen. That will cancel that out. And of course, it's 1 mole for every 32 because it's oxygen, 2 oxygen atoms. All right, now I'm in moles of oxygen. Okay, now I can start my rearranging because I'm on the molar highway. Well, what am I looking for? I'm looking for water, so let's change the identity. Let's go from moles of oxygen to moles of water. Because once you're in moles, you can do that. You can do anything. What's my relationship? What numbers are going to go here? They come from this. So oxygen is 5. Water is 4. Okay, so now we are in moles of water. Almost there. But the question did not ask for moles, it asked for grams. So you have to convert back. Call it the off-ramp of the molar highway. So we're leaving the molar highway. Moles of water goes on the bottom, grams goes on the top. What's our relationship? It's 18.01 grams of water for every mole. We will cross out moles, and there you go. So there's the unit you're looking for, grams of water. We do the math. Again, do these in one step. Don't stop and write anything down. So 7.95 times 4 times 18.01 equals, divided by, I have a parenthesis, and it's 32 times 5, right? It's this times this, exit parenthesis, equals 3.5795 grams. Okay, I have 3 sig figs there. I have 3 here. That does not count. I have 4 here. I'm multiplying and dividing, so I count. So it's 3 sig figs, which is that. So my answer is going to be 3.58 grams of water. If we go back to the slide, right there. So the answer is B. See that? So remember, this is a theoretical yield. This is your calculated yield. No interference, no human error, nobody dropped anything, nothing, no propane leaked into the air. So this is your calculated, therefore it's called theoretical. So I am going to stop here. So I will start the next lecture. So it'll be lecture 11, part 2. I'm going to cover percent yield. We'll work through that, but I'm also going to cover down here is a little more about using energy, stoichiometry with energy, that kilojoule unit, and endo and exo, because you will need to know that. So part 2 will cover those areas. Okay. All right, so see you next. So this is the end of lecture 11, part 1. And then continuing on the same topic for lecture 11, part 2.